Hi everyone, my name is Juncheng. Today, I'm going to show you that FIFO queues are all you need for cache eviction. This is joint work with Yazhuo, Ziyue, Yao, and Rashmi. Software cache has seen ubiquitous deployment in the past decade. This is just a short list of the common software caches being deployed in today's system and infrastructure. There are many types of software caches, such as page cache, block cache, database buffer pool, key-value cache, object cache, etc. When we talk about these caches, we usually care about two metrics. One is called efficiency or effectiveness, and this is measured by miss ratio. The other one is called throughput and scalability. This is often measured by the number of requests the server can serve per second. While it is not used as a metric, simplicity is also very important for these caches, because having a simpler design means it will need fewer bugs and it will be easier to deploy. And at the core of the cache is the eviction algorithm. So eviction algorithm decides which object should be kept in the cache when the cache is full. So it's very important to have a good eviction algorithm that keeps the most useful objects in the cache so that you can achieve a higher hit ratio or lower miss ratio. Because caching is so important for the performance of a computer system, it has a long history of research dating back to 1960s. And if you look at all this caching research, the history of caching research, most of them focus on LRU or least recently used. LRU maintains objects in a queue with last access order. In order to maintain this ordering, LRU needs to update the metadata upon each cache read request. And this metadata update requires locking. And this lock limits the scalability of LRU. Therefore, LRU is not scalable. And in fact, all LRU-based algorithms, meaning that algorithms that use one or two or multiple LRU queues, are not scalable at all. Besides not being scalable, LRU is also not scan resistant, meaning that it does not have a good efficiency or a good miss ratio. Over the past 60 years, there has been many research trying to improve LRU's efficiency and throughput, mostly on the efficiency side. And these new designs often add more techniques or more tools or more metrics to make LRUs, to reduce LRU's miss ratio. As a trade-off of adding more technique, so you get better efficiency, but you sacrifice throughput and or scalability. So meaning that all these new algorithms, although they have lower miss ratio, they also have lower throughput. On the other hand, engineers try to improve LRU's throughput and scalability, because throughput is important for production systems. This is often achieved by reducing the number of operations per request, the number of locking operations per request as well. There are various approaches such as relaxed LRU, clock variance, frozen hot. The conventional wisdom suggests that this relaxed approach, this reducing the number of operations and locking, often sacrifices efficiency. However, our finding at HoloOS this year shows that this is not true. We find that FIFO queues can actually be better than LRU. If you're interested, you can take a look at our paper at HoloOS. To summarize, state-of-the-art eviction algorithms make trade-off between efficiency and throughput. So they either have they can either have higher efficiency or higher throughput and scalability. So they cannot have both. So how do we achieve both? Let's look at an alternative, which is FIFO. First in, first out. Compared to LRU, FIFO is simpler, it uses fewer metadata, and it incurs less computation Or in other words, at each cache hit, FIFO does not require any metadata update. Therefore, it is also more scalable. Besides all this, FIFO is also flash friendly, meaning that if you want to implement an algorithm on flash, FIFO is your best choice. However, FIFO has one big problem, which is its efficiency. FIFO has a high miss ratio. So the question I want to ask in today's talk is that, can we design an efficient FIFO-based eviction algorithm? We want to keep all the benefits of FIFO while we also want to have a high efficiency. While normally this is not possible, however, we find we can make it happen with this new observation. We find that in cache workloads, there are more one-hit vendors than we had expected. So one-hit vendors are objects that only appear once in the sequence. And then we find that for Ziyue workloads, the one-hit vendor ratio decreases with sequence length. So in other words, shorter request sequence have higher one-hit vendor ratio. You may wonder, why do we care about shorter request sequence, right? We care about shorter request sequence because a cache has to start eviction when it sees shorter request sequence. So it won't see the full week-long or month-long request sequence. And it has to evict after seeing, say, a few hours of request sequence. So that's why we care about shorter request sequence. To give you a better idea, let me show you a toy example. So in this figure, I have 17 requests for object A, B, C, D, E. If you look at these 17 requests, among the 5 objects, one of them is requested once, which is this object E, and the one-hit vendor ratio is 20%. If you look at shorter request sequence, say from 1 to 7, among the 4 objects, 2 of them are one-hit vendors, and the one-hit vendor ratio is 50%, huge increase. If you look at shorter request sequence, say from 1 to 4, then the one-hit vendor ratio will further increase. So this is a toy example illustrating that shorter request sequence tend to have larger one-hit vendor ratio. Now let's look at synthetic Ziyue workloads and production workloads. In this figure, the Y shows the one-hit vendor ratio, the X shows fraction of total objects. Let's first look at the left figure. While the full trace has one-hit vendor ratio almost 0, at 1/10 of the trace, the one-hit vendor ratio increased to 80%. So meaning that 80% of objects in the request sequence are only requested once. So this is for different schools of synthetic workloads. On the right, if you look at the 2 production workloads, we can see that at 1/10 of the trace length, the one-hit vendor ratio is either close to 30% or close to 80%. So this is a huge number, right? I first measured this on over 6,000 traces. So these traces are week-long traces. And I measured the one-hit vendor ratio at 1/10 of the trace length. And the mean one-hit vendor ratio across this over 6,000 traces is 72%. So in other words, 72% of objects in the request sequence are only requested once. So what does this mean for caching? So it means that most of the objects in the cache are not reused before they are evicted. Let's verify this using cache simulations. So in this figure, the Y shows fraction of evicted objects, X shows different cache sizes. So we measure how many times an object has been requested after it is inserted into cache. Frequency 1 means that the object has no reuse after insertion. 2 means it has 1 reuse. We can see that under MSR workload, across different sizes, majority of the objects from eviction in an eviction are not reused. Even at very large cache size, over 50% of objects at eviction are not reused. Similarly, at the Twitter workloads, the number is a little bit smaller, but a significant large number of objects being evicted and not reused. So it's important to evict those objects. Or let me introduce S3 FIFO. Simple scalable caching with 3 static FIFO queues. So as the name suggests, S3 FIFO has 3 FIFO queues: small queue, a main queue, and a ghost queue. The small queue uses 10% of the cache size. It's used as filter to filter out those one-hit vendors. The main queue uses 90% of the cache size, and it's used to store most of the objects. The ghost queue only stores metadata. It does not store object data. Therefore, it is very small, and the ghost queue is to keep track of the objects that gets evicted from the small queue, while if some of them may be potentially popular, it will be we will find it with the small queue because it will get requested in the small queue. Okay, now let's look at how cache hits and cache miss work. For each object in the cache, we associate with 2 bits of metadata. Upon a cache hit, the counter increments by 1 if it has not reached 3. So that's how cache hit works. Upon a cache miss, we want to insert the object into the cache. If the object is not found in the ghost, we insert it into the small queue. Otherwise, we insert into the main queue. Because if an object is found in the small ghost queue, it means that it has been requested in the past, and it gets evicted from a small queue. So we should keep it for longer time. So that's why we insert it into the main FIFO queue. Inserting into the small queue and the main queue will trigger eviction. And eviction happens at the tail because it is a FIFO. We look at the tail object, and for small queue, if the counter is no more than 1, it gets evicted. Then otherwise, it gets reinserted into the main FIFO queue. So in other words, if an object gets at least 2 requests, then it gets reinserted into the main FIFO queue when it is evicted from small queue. The main FIFO queue uses reinsertion to keep popular objects in the cache. So if the count is 0, it gets evicted. If the tail object has a counter more than 0, the counter decrements and it gets reinserted. So that's how S3 FIFO works. So although I described this algorithm using 2 bits counter, however, we find that using 1 bit flag is sufficient for most workloads. Okay, now let's talk about S3 FIFO features. S3 FIFO is very simple and robust because of the static queues. And it's also very fast because for most of the popular objects, there's no metadata update. So cache hits is very fast. Therefore, it is also more scalable because cache hits, there's no global metadata update. There's no logging required. And in terms of metadata, it only requires 2 bits or even 1 bit if you want. And S3 FIFO is also flash friendly because all writes sequential writes. So there's no random writes. And if you want to implement S3 FIFO on flash, you can do it. Also, I described S3 FIFO using 3 queues. However, if we want to implement, we can use either 1 or 2 or 3 queues. For the sake of time, I'm going to skip the details of implementation. If you're interested, you can take a look at our paper. Now let's look at some results. First, let me talk about the setup. So we used 14 datasets with 6,594 traces from 12 companies. So this is by far the largest cache eviction algorithm evaluation. This is millions times larger in terms of request count compared to previous work. So in total, there are over 800 billion requests, 60 billion objects. And these traces are very diverse. They were collected between 2007 and 2023. And they include both block cache workloads, query cache workloads, and object cache workloads. We used two platforms. One is called Carnegie Cache Sim. This is a cache simulator platform. And the other one is Cache Leap from Meta. So implement SIGOPS in both. And to evaluate this huge data set, we performed the evaluation on Cloud Lab. And we estimated that over 1 million core hours were used to perform this evaluation. All of our data and software are open source, and you can find it on GitHub. Because we have so many traces, we can't show the distribution curve for each trace. Otherwise, it's going to take hundreds of pages, right? So we use the metric called distribution reduction from FIFO. So basically, we use FIFO as a baseline. We calculate the distribution reduction. And then we compare the reduction between different algorithms. That's for efficiency evaluation. For throughput, we just use the minimum of operations the cache can serve per second. Now let's look at some results. So this figure shows distribution reduction from FIFO on y-axis, different state-of-art eviction algorithms on the x-axis. For the sake of time, I'm not going to explain each algorithm. If you're interested, take a look at the paper. Now I'm showing the mean distribution reduction for different algorithms. We can see that SIGOPS is either it's the best algorithm, although it's just slightly better than the second best algorithm, but it's still the best, right? Now, so that's the mean value. This shows P25 and P75. So this means that for 25% of the traces, SIGOPS can reduce FIFO's miss ratio by up to 22%. And for 75% traces, SIGOPS can reduce the miss ratio by around 7%. At least 7%. Yeah. So that's SIGOPS. Compared to state-of-art eviction algorithm, SIGOPS is still the best. Although the difference between SIGOPS and state-of-art eviction algorithm is not large. However, do notice that this is an evaluation on over 6,000 traces. In order to push the mean value or the percentile a little bit higher, it's actually non-trivial. This further shows the P10 and P90. We can see that SIGOPS is again the best. Putting all together, SIGOPS is the best eviction algorithm among all state-of-art. Although the improvement compared to the next best is relatively minor, but I want to remind you again, this is over 6,000 traces. If you look at a single trace, we can easily find a trace that improves over LU by 60% or improves over arc by 60%. So that's the overall distribution reduction results. So next, let's look at per dataset, because each dataset has different number of traces. Some of them have a few traces, some of them have a few thousand traces. So it's important that it's important to look at per dataset result. In this figure, Y shows the dataset, X shows the mean distribution reduction from FIFO. I haven't shown S3 yet. We can see that on different datasets, different algorithms perform the best. Sometimes there is tiny LFU, sometimes it's nervous. Let me show S3. So this is S3. We can see that on most of the datasets, S3 is actually the best algorithm. When S3 is not the best algorithm, it's often close to the best. Specifically, on 10 out of these 14 datasets, S3 is the best algorithm. This shows the robustness of S3. As a FIFO-based eviction algorithm, S3 comes with superior scalability. So in this figure, Y shows throughput, X shows the number of threads. And I'm comparing S3 with LRU, optimized LRU, and optimized tiny LFU from Meta Cache. And I'm also comparing it with Zcash, which is a new design that achieves code-linear scalability that use algorithm and system co-design. and this requires a log structure design. We can see it compared with all algorithms or all systems. SOSP is the fastest algorithm on a single thread because for most of the requests, SOSP performs no update, no mandate update. And at 16 threads, SOSP is more scalable than the optimized LU because scalability is so important. CacheLib team doing a lot of efforts to optimize the scalability of LU. Compared to this optimized version, SOSP achieves 6 times higher throughput at 16 threads. Compared to Zcash, it achieves similar throughput and scalability, while it does not require any code design or requires a log structure design. So that's the throughput and scalability of S3 platform. Well, due to time limit, there are more content in the paper that I do not have time to talk about. If you're interested in why S3 platform is effective, the input indication for flash cache, dynamic results, the impact of FIFO queue size, and what if we replace FIFO with LU, you should take a look at our paper online at our ACM. So as a takeaway of today's talk, I talk about one-hit wonders, and I showed that cache workloads exhibit high one-hit wonder ratio. And most of the objects in the cache are not reused before they are evicted. So therefore, it's critical to remove those one-hit wonders very quickly. I introduced a new algorithm called S3 FIFO, simple scalable caching with 3 static FIFO queues. S3 FIFO uses a small FIFO queue to quickly filter out one-hit wonders, and use reinsertion to keep popular objects in the cache. S3 FIFO has already been adopted at Google VMware Cloudflare Red Panda and a few other companies. And on the open source side, S3 FIFO has been implemented in many open source cache libraries, and it's available in more than 10 programming languages on GitHub now. So whatever language you use, you'll find a caching library of S3 FIFO available for you to use. So that's my contact. If you have questions, feel free to email me. And if you want to learn more about S3 FIFO, here is the website. With that, I'm happy to take questions.
Just a few questions because we are running late now, but okay, see. Over there.
Okay, thank you. Can you hear me? Yeah. I'm Wei Junyu from Tsinghua, and thanks for a nice talk. So I have 2 questions. My first question is that S3 FIFO shows a better result on many cases, but it still shows a worse result on some special cases. So how can the users to decide whether they will use S3 FIFO if they have a specific trace? So can you give some intuition or some suggestions? And my second question is about, do you have any evaluation of the mixture of different traces? How will S3 FIFO perform in the mixture of different traces? Thank you.
Yeah, thank you for the great question. So for the first question, in our extensive study on over 6,000 traces, we do observe around 1% of the workloads, S3 FIFO is not as good as CFRs. But however, we summarize those patterns where S3 FIFO may fall short in our paper. But to summarize that, so S3 FIFO does not work well if the cache size is super small. So, for example, if the trace or the workload itself is, say, only has a few thousand or tens of thousands requests, and the required cache size, say, is hundreds or a little bit over thousands, then in that case, S3 FIFO does not work well because the small FIFO queue is too small. That's the only cases where S3 FIFO does not work well. On the second question, sorry, what's the second question?
It's a mixture of the traces, not just
mixture.
Yeah.
So so the mixture of workloads. So among the 6,000 traces, I think there are at least 100 traces are multi-tenant workloads. Oh, wait, more than that. At least, yeah, all the block cache workloads are multi-tenant workloads. While for the web workloads, some of them are also multi-tenant workloads. So it's kind of a mixture of different workloads.
Okay.
We didn't like mix workloads by ourselves, but I wouldn't expect it to be significantly different from those already existing multi-tenant workloads.
Okay, thank you.
I hope that answers the question.
All right, thank you. So just the last two, hopefully, questions. So starting on the side.
Peter Desnoyers, Northeastern. Interesting work. I'm curious, the main queue, which is essentially clock, do you know what the typical recycle rate is? Because in particular, that has to do with, as you say, if it's strict FIFO, it's flash friendly. However, it's obviously not if you're with a non-zero recycle.
Yes, a great question. So in our observation, because the traces are very diverse, we do observe very high recycle ratio, meaning that like most of the objects are reinserted, but it varies, depends on workloads. I don't have a number for the mean value, but I won't expect a significant number of objects being reinserted for most workloads.
All right, thank you.
But
Last question.
talking about Flash, it's still better than LU.
All right, last question.
Hi, Micah from UC Berkeley. Yeah, a great talk. I was just wondering if I noticed earlier that the construction of S3 FIFO was dependent on this one-hit wonder ratio, which seems a bit specific to a high-skew Zipfian workload. I was wondering if any of the workloads you evaluated on didn't have this exact distribution, or just generally how S3 would perform in different distributions or without such high skew.
Thank you for the question. Yeah, S3 FIFO is leveraged the observation that most cache workloads have high one-hit wonder ratio. We observe that the high one-hit wonder ratio does not, it's not strongly dependent on the skewness. For example, can you see the figure? Yeah. So the left figure shows synthetic Zipfian workloads with different skewness. Even when the workload is not very skewed, say the blue one, S3 FIFO still has a very high one-hit wonder ratio.
All right, thank you.
Yeah, thank you for the questions.